ready to go?
Hello everyone. We're very happy to have Donagi today telling us about the rationality of intersection of three quadrics. Thank you, Ron.
Thank you, Max. And yeah, I'm happy to be here too. I used to be a student here about 6,000 years ago. So it's always nice to come back and visit. So this talk is going to be mostly math. It's based on some small amount of physics, which I'll try to point out, but it's not going to be a physics talk. It's definitely going to be a math talk, so my apologies for that. So this is a joint work with Tony Pantev. The question is this. If you have a space X, a variety, we say it's rational if there's a map from projective space to it, which is birational, so of degree 1 generically. We say that it is, well, equivalently, the function field is just a purely transcendental field, no algebraic relations. So we say that X is unirational. By the way, can people hear me okay? Great. Let me know if my voice trails off. X is unirational if there's a dominant map from projective space onto a dense open subset of it. So a long-standing question in algebraic geometry is whether unirational varieties are necessarily rational. And if not, how far can they be? So back in the, I think it was late 19th, maybe early 20th century, Lorth proved that the answer is affirmative in dimension 1. It's very easy. You just come up with an invariant, namely the genus of a curve, which decreases under maps. So if the top space has genus 0, then the target space will have genus 0, it will be rational. So that's all there is to that story. Beep goes on, does that mean I'm doing something wrong?
No, that means somebody's joining the call.
Okay. Okay. A similar but slightly more elaborate answer works in dimension 2. It follows from the classification of surfaces. I think it's due to Katzarkov. You have simple criteria that tell you when a surface is rational. You can just check that those are preserved under forward maps. So 1972 was a big year for the subject because 3 different teams of mathematicians proved that the answer is negative in dimension 3. So one of those was Clements and Griffith. They showed that the intermediate Jacobian gives a birational invariant. The actual invariant is the intermediate Jacobian modular Jacobians of curves, which is a little tricky to get used to. And in particular, they showed that the cubic threefold is unirational but not rational. Let me take a minute off and to draw a picture. So here's your cubic. It's known that every cubic contains a line. Even every cubic surface contains a line. So every cubic surface contains a line. So let's call the line L. Let P be a point here. The tangent that's an X is the cubic. So the tangent that P to X is a plane. And you take the union over P and L of these tangent planes. So that's a 3-dimensional variety, which is clearly rational. It's a vector bundle over a line that makes it rational. And that maps onto X. Namely, given the point and a tangent vector, it determines a projective line in P4. That line meets the cubic in 3 points. 2 of them are at P because it's a tangent, so there's just one remaining point. So we send it to that point. So that gives you explicitly a map from this thing, which is rational, to X. If you're bored with the talk, you can entertain yourself by calculating the degree of this map. Yeah. So it is unirational, as I showed there. The intermediate Jacobian is a certain abelian variety of dimension 5, which has it's a principally polarized abelian variety, so it has a theta divisor. And you can easily analyze the geometry of the theta divisor. It has a unique singularity at 0. And the tangent cone at that point is exactly the cubic threefold itself. You can recover the cubic from it. On the other hand, if you have the Jacobian of a curve, it's known that the theta divisor is singular in codimension 4 or less. And if it's product of curves, it's singular in codimension 2. So that shows that the intermediate Jacobian of the cubic threefold, whatever it is not the Jacobian or product of Jacobians of curves. Why do curves come in? Because if the thing were irrational, you could get it from P3 by blowing up, doing a series of blow-ups. And the things you blow up are going to be curves. P3 does not have any abelian differential. Its Jacobian is trivial. So at each step, all you do is you're adding the Jacobian of the curve that you're blowing up. So that's why you're getting a sum of Jacobians of curves. So the fact that we understand the geometry of the intermediate Jacobian of the cubic threefold allows us to conclude that the cubic threefold is not rational.
Well, that's for any dimension, right?
This is for dimension 3, cubic threefold. Did I not say that? Well,
Okay, some more details for dimension 3.
yeah. Everything on the rest of this page is only in dimension 3. So another example was given by Mumford and Alten. They showed that torsion in the third cohomology is a birational invariant. So then all you have to do is to exhibit a particular unirational variety which has torsion in its cohomology, and you're done. So let me just use the opportunity to introduce classical terminology. A pencil means P1's worth of something. So pencil of lines is a one-dimensional family of lines. A P2 is called a net, and a P3 is called a web. So if I say a web of quadrics, that means a family parameterized by P3 of quadrics in P3. A quadric in P3 determines two objects, the two rulings on that quadric. So given the family, you get this way a double cover of P3. That's the variety that Alten and Mumford looked at. And yet in the same year, Zariski and Mannion showed that quadratic fourfolds are irrational by studying the rational automorphism groups. And some, not all of them, are rational, are unirational. Okay. And the next big progress in the subject occurred this year. So this is Katzarkov, Kontsevich, Pantev and Yu. They developed this theory of Hodge atoms and used it to show that the cubic fourfold is also unirational but not rational. So I'm going to talk about a variant of this that I did with Tony Pantev. It's a different variety that we showed has that behavior, is irrational, using this technique. And it's considerably simpler than the case of the cubic threefold. So hopefully this indicates a way to use this big machinery to apply it in algebraic geometry.
Say again, it's simpler than?
I'm sorry?
It is considerably simpler than which case?
The case that the variety that we're studying is going to be much simpler than the cubic fourfold, which is what KKPY did. Okay. So let X be a very general, smooth, complete intersection of three quadrics. In other words, the base locus of a web of quadrics in P7. So that's a four-dimensional variety. That's going to be our object. Naturally associated to it is a surface S and a gerb alpha on S. I'm going to describe those in detail in a few minutes. And the point is that you can show that the derived category of alpha twisted sheaves on S, on the surface S, is a direct summand of the derived category of X. By studying shift theory of the twist, I'm not doing this very well. By studying shift theory of the twisted surface, we show that the natural non-commutative space attached to X is truly non-commutative. Again, I'll explain what truly means in a second. In particular, it's associated numerical K-lattice is not isomorphic to the K-theory lattice of any smooth projective surface. And that means that the relevant derived category is not equivalent to the derived category of any smooth projective surface, which basically implies the irrationality. So using the new theory, yeah.
No, sorry, that was
So using the new theory of Hodge atoms, I guess I could face the audience.
Let me try and configure the sound. Keep going, don't mind.
Okay. So using this new theory of Hodge atoms, this reproves the irrationality of a very general intersection of three quadrics in P7. There is a very different purely algebraic proof due to Hasid Furutkan's and Schinkel. So I'm going to make some philosophical remarks which may or may not be very useful. So let me go through those a little quickly. Shift theories of GM gerbs are, in general, very interesting for a variety of reasons. For example, they contain essential information about the complexity of Broward classes. They serve as a common playground for geometric constructions, for presentations, and most pertinently for us, they provide standard examples of non-commutative spaces, or NC spaces for short. So the thing that one studies are triangulated C-linear differential graded categories. These categories are viewed as digi versions of the categories of quasi-coherent sheaves. And since we don't have the actual geometric object of a non-commutative sheaf, of a non-commutative space, we just take the derived category as representing the space itself. The categorical point of view towards NC geometry allows for unified treatment of complex and symplectic manifolds, as well as quantized and stacking geometries of various sorts. Geometric properties such as being algebraic, proper, smooth, Calabi-Yau, and so on are notions that are intrinsic to the derived category. So you can state them without having the geometry. Moreover, the cohomology groups of smooth and proper NC spaces can be enhanced with additional algebraic data, which is called the pure non-commutative Hodge structure, developed in their previous work. So this is not just an abstract theory, it contains classical algebraic geometry. Classical algebraic geometry fits within this formalism as a classical scheme or an algebraic stack, may be regarded as an NC space for which the corresponding category is just the derived category of quasi-coherent sheaves on the space. There are many other examples of NC spaces coming from geometry or physics. For example, Fukaya categories of symplectic manifolds, matrix factorization categories, Fukaya Seidel categories, and so on. Okay, I can skip that. And so an important class of NC spaces comprised of the NC spaces of geometric origin. by definition, those are given by category C, for which perfect C, the perfect complexes of C, admits an embedding as an admissible subcategory in the category of some geometric object, some scheme. So examples are equivalence of components of Fano manifolds, residual categories of spherical functions, derived categories of twisted sheaves. And the last one is the one that we'll be most interested in. So it's expected that truly non-commutative NC spaces of geometric origin will be birational invariants of projective varieties on which they live. So in general, you can look at equivalence of components. Those are basically direct summands of the derived category. Can frequently be distinguished from smooth projective varieties. The difficulty here is that it's harder to come up with non-commutative spaces that are associated to gerbs that have this property. So let me explain why this is tricky. So let's work with K3 surfaces, or two-dimensional Calabi-Yaus. So to illustrate the point, we call that for any smooth projective variety X in an unified Brauer group alpha, Brauer class alpha, we have the category of alpha twisted coherent sheaves on X. So that means, well, what's a sheaf? A sheaf means that you assign something to each open set, and then on the overlaps, things match exactly. An alpha twisted sheaf means that instead of the product of three transition functions in a row gives you one, it gives you the representative of the class alpha. Alpha is a Brauer class. So this category embeds as an admissible subcategory in the variety of alpha. So the way that gerbs are usually described in algebraic geometry is you have a variety, and you have a P1 bundle over it. And you ask, is the P1 bundle projectivization of a rank 2 vector bundle? It doesn't have to be P1, it can be Pn for any n. So you have a family of projective spaces. You want to know whether you can lift the structure from PGLN to GLN and get a vector bundle represented there. So if you cannot, that means that this bundle represents some non-trivial Brauer class. So roughly speaking, an alpha twisted sheaf downstairs is a sheaf upstairs with some trivializations along the fibers. So it is geometric, but unfortunately it can happen that the non-commutative space, so let's call it alpha x, or for the alpha as a subscript on the left. It can secretly be commutative, even though it doesn't look like it. So as soon as X is a smooth projective K3 surface, which happens to be elliptic, so it comes with an elliptic fibration over P1. In this case, one knows that there's the canonical identification of the Brauer group with the Teicher-Forevich group, which is an object with Teicher-Forevich group is another elliptic fibration, which fiber by fiber is isomorphic to the given one, but is globally different. In other words, you don't have a section. If you had a section, that would make it isomorphic to the elliptic fibration. So those things form a group. So you can, yeah. So each element alpha in the Teicher-Forevich group is realized by a smooth projective K3. So we'll call this one X alpha with alpha on the right, which is fibered by genus 1 curves and has Jacobian fibration, the original X. For a sheaf on the fiber product of alpha X and X alpha, this is an equivalence of categories between them. So the conclusion is that the non-commutative space alpha sub x is secretly isomorphic to the category of the classical space, which is just this other K3 surface. So this phenomenon shows that the question of recognizing whether an empty space corresponding to a category of twisted sheaves is truly non-commutative is quite subtle. Questions? Yeah.
So in a string theoretic context, would this be analogous to the statement that if I considered compactification on K3 with some B field turned on, that's dual to some purely geometric compactification?
As long as the K3 is elliptically fibered.
As long as it's elliptically.
Yes.
Okay, thanks.
Yeah, so that's, yeah, well, that's a theorem of ours. So the basic method for distinguishing NC spaces from commutative spaces is due to Kontsevich. It boils down to checking that the numerical K-lattice of a geometric NC space cannot be isomorphic to the numerical K-lattice of a smooth projective variety by checking that it doesn't contain points. In other words, the lattice of the K3 lattice cannot contain a class that behaves like the class of a point. I'll explain that. I'll explain what that means concretely in our case. So Kontsevich used this method to show that category of twisted sheaves associated with a very general four-dimensional cubic four-fold containing a plane is truly non-commutative. So within the universe of four-folds, there's a codimension one locus of the one that contained a plane. And those were known to be irrational generically by Kontsevich. But that does not imply anything one or the other for the general one, which is the new result. So in this talk, we use Kontsevich's method to show that the natural NC spaces associated to an intersection of three quadrics in P7 is truly non-commutative. More precisely, the derived category of our X has a semi-orthogonal decomposition, so it has a couple of silly pieces that we throw away. And the key piece is this derived category of alpha twisted sheaves on the surface S. I still have to tell you what the surface S is and what the class alpha is. It turns out there's some surfaces general type, double cover of the plane branch along a smooth octic. That means curve of degree 8. Alpha is a two-Taurian Brauer class on S. In order to analyze the properties of this derived category, there's this lattice that we have to consider. So the group itself is just a cohomology twisted by B, which is a representative of the gerb. I'll tell you in a minute. Yeah, so B is, well, alpha lives in the Brauer group, which is H2 of S with O star coefficients. Since it's an element 42, you can lift it to a representative capital B, which lives in cohomology with half Z integers and the exponential map. So HSBZ is the analog of the Hodge classes, but twisted by the exponential of B. So that's our lattice. And then there's a pairing on it given by the usual stuff with square root of Todd classes and so on. So the Mukai pairing. So up to isomorphism, the lattice lambda depends only on S alpha, not on the representative B that we picked. And we show that this lambda cannot be isomorphic to the Mukai lattice of integral Hodge classes of any smooth projective surface. So the corollary is that.
So may I ask, what is this surface? Is it obtained from as a cover of P2 or?
Of course, yes.
Yeah,
So
because you have the quadrics.
yeah, it's just that. So we have the net of quadrics. It's a P2. The generic point corresponds to an 8 by 8 symmetric matrix, which is the quadric. So it has two rulings. You keep track of those two rulings over the net, you get double cover over the plane. It'll be branched along an octic because the determinant of the 8 by 8 matrix is of degree 8.
That's a general term. Thank you.
So the theorem says that S alpha be the associated surface of general type with two-toed vacuum, then the associated numerical K lattice is not isomorphic to anything coming from a surface. So okay. So let me make a detour and tell you a little bit about the KKPY opus. So we start with X, a smooth variety, smooth projective variety. And you associate to it what they call an F bundle, which is some version of a Frobenius manifold. I guess F stands for Frobenius. So it's a non-Archimedean variation of A-model non-commutative Hodge structures. Yeah, I can't suggest that either. But I can break it down into a few pieces. So the base of this bundle is just the ordinary Betti cohomology with rational coefficients. And you think of that as a supermanifold. You forget the integer grading of cohomology, you just take the Zimmer-2 grading, even in odd classes. There's a Novikov ring, which is a formal power series in a bunch of variables. And the basic of Gauss-Witten theory is that there's quantum multiplication. It's a map from H, tensor H, to H, power series in these Qs, and one other and further variable T that are coordinates on the cohomology. So this is called quantum multiplication. And it's a deformation of the usual cup product. So if you just kill the deformation parameters, the basic map H equals H to H is just cup product. But then it's a deformation, and if you write down the coefficients of the deformation, those are the numerical invariants, the Gauss-Witten invariants. And this H is a Frobenius manifold. So back to F bundles. An F bundle is a variant of Frobenius manifold. So it's a triple H nabla over B, where roughly speaking, and unfortunately I can only be rough here, there's a field K, which is something like the p-adics. It's a non-Archimedean field. B is going to be a K-analytic supermanifold. There's going to be a D, which is the geometry origin of an analytic disk with coordinate U. So the actual base is going to be the product of B cross D. And the bundle H is going to be a K-analytic vector bundle over B cross D, together with a connection nabla, a flat neuromorphic connection. It has poles only at U equals 0, U is the coordinate on the disk, and it has to satisfy some further conditions, which I'm going to skip. The point is that this gives you a spectral decomposition. There is a distinguished vector field downstairs called the Euler vector field, which roughly gives the grading. And you can look at quantum multiplication by it. That's an endomorphism of the cohomology, depending on these parameters. So you can look at its eigenvalues or eigenspaces. So the spectral decomposition is decomposition into generalized eigenspaces. And what we actually want to keep track of are just eigenvalues. So an easy example is, let's take X tilde to be the blob of X along some subvariety Z of codimension R. Then we know that the cohomology of X tilde is the cohomology of X plus a bunch of copies of the cohomology of Z shifted by 2I, where I goes from 1 to R minus 1. Because we're replacing each point of Z by a projective space, PR minus 1. So after linear combinations, this is the eigenspace decomposition over a point B, which corresponds to the pullback of the ample class, n ample class on X. Remember, this depends on the point in cohomology. So over the pullback of the ample class of X, you get this decomposition. But the point is, you can go to nearby points and you may get a refinement of this decomposition. So there are some new invariants that you're going to start seeing. anyway, Hodge atoms are what you get when you restrict the F bundle to just the Hodge classes, into rational PP classes. So you get a spectral cover of this variety. And a Hodge atom is basically an irreducible component of that. So that variety is a finite cover of the base. You throw away the ramification. So now you have an entire cover of an open set. You take its connected components.
So by base now you mean after
The
taking
Hodge
product-
class.
After taking the product with this formal, after taking the product with the disk, is that what you mean?
I think the base I want is just the Hodge cohomology.
So can you say, so what did you mean by the decomposition can become more refined than nearby points? What? H2 of x contains some ample class and pi x tilde to x. So pi of star of L gives me a particular class in H2 x tilde. But this class is not ample on x tilde because it collapses Z. Class by class. Okay, I understand.
So I
if
just
you vary
deform to nearby points.
Okay, thank you.
So Iritani has a blow-up formula that is relevant in these cases. And this implies the irrationality criterion. If x is rational dimension D, each of its atoms comes from a variety of dimension less than or equal to D minus 2. So this is a generalization of what Clements and Griffiths did. They used the intermediate Jacobian to show that if you have a three-dimensional variety that's rational, then its intermediate Jacobian comes from curves. Same here. The point is that if it's rational, you can get it by a series of blow-ups, and what you blow up in each step has to be of codimension 2 or higher. So if you can show that you have an atom in the composition of X, which does not come from lower dimension varieties, then you win. How late can I go?
Fine.
About two?
If not half an hour.
Okay, great. Yeah, so this is analogous to the Clements-Griffiths result. But it's more powerful, and so it works in higher dimensions. There exist enhanced versions of Hodge atoms. Technically, we're not using Hodge atoms in our work. We're using some slight enhancement, but never mind the details. So to finish my introduction, the fact that lambda is not isomorphic to the Mukai lattice of a Hodge class of a smooth projective surface has these applications. So I've said most of this already. Yeah, so we just construct this lattice lambda. We show that it does not come from any surface, and therefore the very general intersection of three quadrics cannot be rational. Okay, so forget the theory. Now let's just play with classical algebraic geometry. So we're going to consider the Fano forward X, which is the intersection of Qt. So let A be the parameter space of my net. So A is isomorphic to P2. Yeah, A is P2. Embedded into the space of all quadrics in P7, which is some big projective space. So, and X is the intersection of those quadrics. We will assume that A is sufficient general, so that singular quadric, well, first we want X itself to be smooth, and we want the singular quadrics in the net, each of them should be only minimally singular, only one singular point, so coordinate 1. And the discriminant curve given by the determinant of this 8 by 8 matrix should be a smooth curve of degree 8. So it's a plane arctic. And then, as we've already said, the surface S is going to be the unique double cover of A branch along this discriminant curve. So it's easy to see that just like the cubic fourfold, the complete intersection of quadrics also contains lines. So we fix, for instance, for a general line L in X, which does not intersect the curve of singular points. So we're going to consider this incidence variety. So this is contained in A, Katzarkov-Riemannian. The point of A is well, it's T, but it represents a quadric Q sub T. A point here is a plane, let's call it pi. I want to look at those pi's that contain L. L was the one line that I fixed. And now contain QT. So it's an incidence variety. This Y fibers over A by the first projection. The general point T and A determines P sub T is going to be a 5-dimensional projective subspace. Namely, at each point of X, I take the tangent space to the quadric. That is a hyperplane. I take the intersection of all of those. That's a one-dimensional family of codimension 1 spaces. The intersection is codimension 2. So that's a P5. That little PTB, that P5, modulo L. By construction, that P5 contained my line L. So there's a quotient, which is a 3-dimensional. I guess it's a sub-quotient of the original P7. In NPT, I have a quadric QT, which is induced by the original quadric. So this is a very general construction you can do if you have a quadric and a linear space contained in it. You can construct a new quadric whose rank is the number of variables is if your subspace was a projective space of dimension k minus 1, meaning it was spanned by k objects, then you've reduced the number of variables by twice k. Group theoretically are going from the group SO2n to SO twice n minus k. So the incidence variety Y fibers over A, and the fiber over a general point of A is isomorphic to the quadric surface, little QT. So that's why I introduced it. On the other hand, I claim there's a birational isomorphism between Y and X. Remember what X was? The intersection of the quadrics. Remember what Y was? Let's go back. Y is this incidence variety. So it maps to A, and it sits inside A Katzarkov-Riemannian. So it's a very explicit map. I think maybe in the interest of time, I'll skip the details. So I'm just showing that starting with a pair T pi, which is a point of Y, I do some intersection and stuff, and I get a point of X, and conversely, I can start with the point of X and describe the point of Y. Our genericity assumption on A and on L implies that our Y is smooth, and then the discriminant curve for the family Y over A. So remember, the family Y over A is a family of quadric surfaces instead of quadric sixfolds. But nevertheless, its discriminant is going to be an arctic. In fact, the same arctic that we had before. So the general property of this reduction is that if you start with a smooth quadric, you reduce to a smooth quadric. If you start with a singular quadric, you reduce to a singular quadric. So it has the same discriminant curve as the original. Here I'm
I'm trying to prove it. So, like I said, it's a general construction. Sometimes it's called hyperbolic reduction of the family. So the total space of our family of six-dimensional quadrics is a divisor of by degree 1, 2 in A cos P7. A is our P2. So we can think of this as a family of 8 by 8 symmetric matrices parameterized by A, whose entries are like linear forms on A. The discriminant divisor gives the discriminant divisor of the map is given by the determinant of the family, which is a polynomial of degree 8. So how can it be that we said that if we have a family of quadrics in P7, the discriminant will be an octet. Here we have a family of much smaller quadrics. There's a quadrics in P3. So how come their discriminant is still an octet? Well, the point is that those P3s are not fixed. They move. And that's going to contribute to the degree. So we do some calculation, and I think I'll skip some of the details. But we say the key is that the bundle in question, instead of being completely trivial, it's the sum of 2 copies of O minus 1 and 2 copies of O. And that's what jacks up the degree to 8. So I'll skip the calculation. Okay. So now consider the double cover of pi from S to A. It parameterizes the rulings on the fibers of the quadratic surface. By construction, S is a smooth surface, which is a double cover of A, branch along the discriminant delta D. But then the universal ruling gives us a P1 bundle R over S. So this is key. What am I saying? I'm saying a point of S gives me a quadric surface in some P3. That quadric has 2 rulings. So I give me the 2 points. Tracing them gives me S. But if instead I take the set of all lines, it gives me a P1 bundle over the double cover. That P1 bundle is going to be the Brauer-Severi variety. That's the thing that determines the job. Questions? So we got a P1 bundle R over S, R for ruling. So that's about Severi variety over S. So let alpha be the class of this thing in the Brauer group. So by definition, this alpha is a 2-torsion element, which can be viewed as a class of a sheaf of rank 4 as my algebras of S, if you want. We're not really going to use that point of view. So note that for very general choice of the net A, the surface S will be net Lefschetz general, meaning that it'll have only the Hodge classes that you see on it. And so we'll have Picard equals one-dimensional Picard group generated by the hyperplane line bundle. So call that H. And by construction, H squared is 2 because we're on a quadric. So again, there's a fair amount of explicit calculations. Which shows that if let C and S be a smooth curve in the linear system H, That's the generator of the Picard. Then the ruling, which is P1 bundle, restricted to C, is isomorphic to projectivization of W for some rank 2 vector bundle W. And so we're using this brace for fractional part. So B times H is a rational number. We take its fractional part. And it's just going to be half the degree. So if the vector bundle W has even degree, this will be an integer. If it's odd degree, it will be half an integer.
Sorry, what is B?
What is?
B?
Yeah. So B was an explicit representative of the class alpha.
Okay.
So alpha is an H1 O star. B, I'm sorry, H2 O star. B lives in H. Where is B? Yeah. So B is an H2 of S with half the coefficients. And this is an exponential map. So I guess my sequence is O star goes to O star, kernel Z1, 2. I have a class in H2 of O star. It's a class of order 2, so it dies here, so it lives to some class in H2 with half the coefficients. That's what we call B. So we calculated, we show that in the section of B with H is, well, it's a non-integer. It's half plus an integer. And the section of B with itself is independent of the choice of B. And in a minute, we'll compute what it is. Yeah, so the construction is pretty, but I don't think I'll be able to do justice to it. So you just look very carefully at the behavior of the fibers and the various involutions, and you count how many exception points you get, and at the end of the day you get 8 of one kind and 5 of the others. That gives you 13, which is an odd number, so it's not 0. So if you believe all that, the 8 and the 5, the 8 dies, the 5 gives you the non-zero entry. So here's what we know about the surface. It's a smooth, simply connected surface. It's of general type. These are the Hodge numbers. Its Picard is the integers. It's generated by the hyperplane line bundle, which is the pullback of O1 on the plane. In fact, this pullback is the canonical class of S, and the morphism pi is given by the complete canonical inlet system. It's just the canonical map. And we can compute C1 and C2. They are what they are. So to conclude, we need to put together the general theory with the specifics of the geometry in this case. So following Hoiberg and others, we know that on the K-theory, there is a natural Euler pairing on the quadratic group given by the alternating sum of the dimensions of the X groups. There's also a Mukai vector, which maps K to the Hodge classes, namely, you take the Chern character of E and multiply by the square root of tau C. So this combines Gordon-Equilibrium statement. And you get the Mukai pairing, which is given by curve product twisted by differential of C1. With this notation, Gordon-Equilibrium formula becomes, says that chi of EF equals this Mukai pairing. Okay, so the free abelian group, together with its Mukai pairing, is called the numerical K lattice. That's essentially the lambda that we work with. It's isomorphic to the quotient of Kz by the kernel of the Euler pairing and derived invariant of Z. So if Z1 and Z2 are smooth projective varieties with non-isomorphic K lattices, then the derived categories cannot be equivalent. So we need a slightly different version, which takes care of, which incorporates the gerb, the alpha class. And it goes basically the same way as the usual pairing. So suppose that we have our double cover pi, S to A, branch is very general octet. Let B be a class in H2 have Z coefficients, which lifts alpha. And consider the bound derived category of alpha twisted coherent sheaves on S. So similarly to the untwisted case, we get the Euler pairing on the Gotthard group, and the choice of B, as before, gives us a way of computing the Euler characteristic in terms of characteristic classes. Namely, there exists a B-twisted Chern character, which is a linear map from the K-theory to the cohomology. The image of the B-twisted Chern map is a finite index subgroup in the free abelian group HSBZ, which is the XB twisted version of the Hodge classes. The alpha twisted Euler pairing is computed by essentially the same formula as before. Well, the only change is that V is the B twisted Mukai vector, and the pairing is the Mukai pairing. So we define it in terms of alpha of B, but it depends only on alpha, and the choice of B gives you the embedding into the full cohomology. So following Kontsevich strategy, we would like to argue that the numerical lattice cannot be isomorphic to the numerical K lattice of any smooth projective surface. So what we're going to do, I'm going to show you that you cannot have a class that would be the representative of a point. So we show that this Hodge class, this Hodge group is a finite index subgroup in the free abelian subgroup, whatever it is. And we compute explicitly the pairing in the basis. We get the ground matrix for the pairing. Here it is. So you just compute. And then you just plug the given, the explicit ground matrix for the pairing. And you compute the group V squared, and it turns out to be 3/4. So correlate. Well, we know that BH is half and B squared is 3/4. So there are no elements V1, V2 in the numerical K lattice with the property that the intersection is 1 and the subintersection of one of them is 0. That's what we would have to have if we had the class of the surface and the class of a point. The product should be 1, and the subintersection of the class of a point is 0 for dimensional reasons. And we're just showing that in the particular lattice, there are no two classes with that behavior. Okay, so again, it's a little calculation. Putting it all together, that shows that the associated numerical K lattice is not isomorphic to anything coming from a smooth projective surface. Well, yeah, I understand. So, thank you.
Questions?
Could you say again how you get from here to the conclusion that, so now you apply the theory of Hodge atoms?
Yeah.
Right, but how do you apply it to the derived category rather than the Hodge structure?
Right. So the derived category of the variety had a couple of silly direct summands. And one of those, the only non-trivial piece is the twisted derived category of the surface S. So now the question is there a smooth surface without a germ whose derived category is equivalent to that of this twisted thing? So I gave you the example earlier on. In the case of K3 surfaces, you can have a germ on a K3, and the derived category is equivalent to some other K3 without a germ. But in this case, we show that this cannot happen.
So so for a general cubic fourfold, if you knew that there is this Kuznetsov component, right, which also looks like a derived category of a surface where we don't know whether it is or not.
That's
If you could show that it's not, then the same theory kicks in to tell us that.
I believe that's exactly what KKPY do.
Uh-huh.
So they proved the irrationality of a very general cubic fourfold.
I mean, I was surprised that they seem to not mention derived categories at all. I mean, they just go through to the Hodge structure directly. So here it seems like we're taking a slightly different.
Yeah. And for one thing, we actually finished this project before they did theirs, but that's where we clearly rely on the result. Yeah, I mean, I think I do not fully understand what they're doing with the cubic fourfold, but it seems that our approach is considerably simpler and shorter.
Further questions? Okay, let's thank Ron again.
fact about K3 was cool. I hadn't appreciated